So there are two ways of describing fluid motion. There are two ways of describing fluid motion. The one is Lagrangian description, and second is the eulerian description. Okay, so let's study about Lagrangian description first. So let's consider a fluid, let's say in this container. Okay, I have fluid. Okay, now if I am interested in how a particular, let's say there is this small fluid element. Okay, so now let's say if I am interested in knowing how this fluid element is moving with time, what is its trajectory. So let's say it moves, let's say just me just draw it with some other color. So let its trajectory be like this. So after a certain time, let's say the fluid particle is somewhere over here, this, let's say the fluid. So let's say this fluid element reaches here in time t plus delta t. Okay, so if I'm basically tracking the individual fluid element, that how does it move over time in space, then this description is called the Lagrangian description. Okay, so let me just quickly write it. So in Lagrangian description, we are observing individual fluid element and its motion. Okay, so this is what a Lagrangian description is. Okay, now let's study about what is a eulerian description. So in eulerian description, we are interested in knowing how fluid properties change as a function of time for a fixed point. So let's say I am interested in knowing, let's say let's say I have this point, and now I am interested in knowing that with time how the fluid property would change. So what would be the velocity vector of the fluid across this point, what is the pressure value, so on and so forth. Okay, so in eulerian description, I am not interested in individual fluid parcels. I am interested in knowing the properties of the fluid at this point. Okay, so let me just quickly write it. So in eulerian description, we are not interested in knowing how a fluid element moves, rather we are interested in we are interested in knowing how fluid properties change over time for a fixed point. Okay, so fixed point can be anything, so that is what we will define. So let's say this can be a fixed point, this can be a fixed point, this can be a fixed point in some space, and we are interested in knowing how the properties change over time by fixing the point and not fixing the volume element in our study. Okay, so I hope the difference is clear to you. Okay, so the reason for describing the fluid in Eulerian description is that the instruments that we build, let's say I have built a device for measuring the pressure value. Okay, the pressure value of, let's say, some fluid. Then that device, I'll put that device in some particular location, right? And I'll measure the measurable quantity like pressure at that particular location with time. Okay, so that's why, because our probes cannot be moved with the fluid parcel or fluid element, we have to describe the fluid in the Eulerian description. Okay, now let's try to understand what is the relationship between the Eulerian description and the Lagrangian description. So let's again consider a fluid. Let's say this is a container and this is my fluid. Okay, all right, so now let's consider a fluid element. Let's say this is my fluid element at time t. Let's say the instantaneous velocity of this fluid element be v vector. Okay, this is the velocity vector of this, instantaneous velocity vector of this fluid element. And now for in time dt, let's say this moves to some other location, this fluid element moves to some other location in time dt with new coordinates. So let's say the initial coordinates were x. So let me just write it with some other color. So let's say the initial coordinates were, let me just write it here. So this was my fluid element with coordinates, initial fluid element, the fluid element at time t in space with coordinates x, y, z, and time t, in time t. So let's not write t. So in space, initially the fluid element was at x, y, z. Okay, then this fluid element has moved with velocity, let's say this, since it has an instantaneous velocity v vector, it has moved to a new location. This fluid element has moved to a new location in time. So this is in time dt, it has moved to a new location with coordinates x plus dx, y plus dy, and z plus dz. Okay, all right, so now I'm interested in knowing, so the question is what is the rate of change of some, let's say, some quantity felt by this fluid element. This quantity can be, let's say this quantity can be acceleration. So if this particle is moving from here to here, what is its acceleration? Okay, this can be some scalar quantity like pressure. Okay, so this can be some quantity. This is some quantity that is changing as a function of time when this particle is moving from here to here. Okay, all right. So that quantity, so since we are how we are describing this fluid, we are concentrating on one fluid element and tracking its motion. So this was my Lagrangian description. So in the Lagrangian description, this rate of change of quantity will be simply dq by dt. Let's say that quantity was q, so that rate of change of quantity will be dq by dt. Okay, I just not write felt, I should write associated with this fluid element. Okay, so let's say the rate of change of quantity q associated with this fluid element is dq by dt. Okay, so this was in Lagrangian description. All right, so now in Eulerian description, what we have, let's just erase this so that I can draw some coordinates. So in Eulerian description, what we have is, we have some fixed points in space, and we are interested in knowing how quantity changes over time at that particular point, right? So let's say if that point coincides with this coordinate xyz. Okay, if one of my points in the Eulerian description coincides with this coordinate xyz, which corresponded to the fluid element at time t, then the rate of change of quantity felt by this point should be equal to the rate of change of quantity that we are describing in the Lagrangian description, right? So this should be equal to dq by dt in Eulerian description. Okay, but what is the difference? So this is in the Eulerian description, but the difference is we have to fix the point at xyz at time t, then only this dq by dt will become equal to the rate of change of quantity in my Eulerian description. Okay, so in that case, this dq will be a function of x, y, z and t, because if my x, y, z and t are not same, this will not correspond to the Lagrangian description, right? Okay, or maybe I can just write it like this will be equal to dq by dt for the coordinates x, y, z at time t for fixed coordinate x, y, z in time t, then only these two will be equal. Okay, but since in Eulerian description this dq by dt depends upon the coordinates, that this dq by dt, any, let's say any rate of change of this quantity in the Eulerian description, it can be different for different points. So let's say at this point I have some dq by dt, at this point I have some dq by dt, for this point I have some dq by dt, and for this one let's say I have some dq by dt. So this dq, this differential rate of this differential change in q is dependent upon what coordinate value that you have chosen, and also what is the time. Okay, so this means that this q in Eulerian description, this q is actually a function of the coordinates x, y, z and t. So I think this is getting confused with this x, y, z and t. So let's just write it as x naught, y naught, z naught. Let's write this as x naught plus dx, y naught plus dy, z naught plus dz, and this is x naught, y naught, z naught and t naught. Okay, and t. Okay, so this q is dependent upon the coordinates that you have, the coordinate of the point in the Eulerian description, and also the time that you have chosen, right? So then we can use the chain rule to write this dq as del q by del x dx plus del q by del y dy plus del q by del z dz, because this q is dependent upon x, y, z and t, and dq by dt would be equal to del q by del x dx by dt plus del q by del y dy by dt plus del q by del z dz by dt. Okay, right? Now we are interested in knowing dq by dt at x naught, y naught, z naught and t. We are interested in knowing dq by dt at a fixed coordinate x naught, y naught, z naught and t, which corresponded to my fluid element. Okay, so this is del q by del x. Now what would be dx by dt? Since at x naught, y naught, z naught and t I had fluid element, right? I had my fluid element, and this had a velocity vector v vector. This had a velocity vector v vector. Okay, and let's just write this v as a bigger v vector. This had a velocity vector v vector, and since this is in 3D, we can write this v vector, this velocity vector, bigger velocity vector, as this will be in x-axis, in y-axis, for which the normal vector is j hat, and will also be in z-axis, for which the normal vector is k hat, with corresponding magnitudes, right? So let's say the corresponding magnitude is u, or we can also write, let's say just write vx, vy and vz, and also some people write it as they write vx as u, vy as w and vz as so this they write it as v, small v, and they write this vz as w. Okay, so it's just a notation. All right, so we just argued that the velocity vector at x naught, y naught, z naught, since this is particle's velocity capital V vector, this should be equal to dx by dt. Okay, so then this dx by dt is nothing but vx. Similarly, we had del q by del y here, we had del q by del z here, and this becomes vy and this becomes Vz. Okay. Now we can further simplify this expression and this dq by dt. So we started this by writing dq by dt in Lagrangian description. ठीक है? Okay. Alright. Now we can further simplify this term. Before that, is there any mistake here? Yes. Since it is dependent on x, y, z and t. So I have written this for x, this for y, this for z, but not for t. So this would be del q by del t dt. Okay. And similarly, we will have a term del q by del t here, since dt by dt will become 1, and this would be del q by del t. Alright. So bringing del q by del t in front will be written like del q by del t plus, so if I write Vx as Vx I hat dot I hat del by del x plus Vy j hat. Okay, it should not be, this is correct. So Vy j hat dot j hat del by del y plus Vz k hat dot k hat del by del z, and take q outside. Can I do that? Right? Yes. Okay. Yes, we can do that, because I dot I will become 1 and this will be written as Vx del by del x, and Vx del by del x times q will become Vx del q by del x, which we had here, and similarly for the rest. Okay. Now if you see here, this expression is nothing but v vector dot grad vector into q, right? Where grad vector was or is I hat del by del x plus j hat del by del y plus k hat del by del z, and v vector is vx I hat plus vy j hat plus vz k hat. Okay. So this dq by dt in Lagrangian description becomes equal to del by del t plus v vector dot grad vector whole times this q. Okay, and this is in the Eulerian description. So we just found a relationship between the Lagrangian description and the Eulerian description for a measurable quantity q. Okay, so for any quantity, let's say the quantity is acceleration vector, so then the acceleration vector, let's say we want to find the acceleration in the Lagrangian description and in the Eulerian description. So how we can write it? Then we will write it like, so this is the acceleration that we want to find for the particle. Then how we'll write it? We'll write del by del t plus v dot grad vector and whole times, sorry, not a but whole times v vector. So this will become del v by del t plus v dot grad v. Okay, so this is how I can find the acceleration of the particle from the Lagrangian description. That is, I can just directly find dv by dt, or I can find del v by del t plus v dot grad of v vector, and adding these two terms will also give me the acceleration of the particle. Okay, so let's try to understand this with some example. Yeah, before that, let me just quickly write what are the names for these terms. So this is generally written like d by dt to tell us that we are in the Lagrangian description of motion. Okay, so it's just a notation. We can write this as d by dt also. Okay, so if you are written, if you see it somewhere, don't get afraid. It's simply the notation, which also means dv by dt. Okay, so this is called the material derivative, material or substantial derivative, and this is for any quantity. So let's just not write that quantity inside this circle. So let's say this is some quantity q. Let's not add acceleration here. Some quantity q, or maybe just write it, let me just write it with some other color so that it is clear. So this is q, and this q would come here, and this q would come here. So I can just write q outside. Okay, so then this is called the material or substantial derivative. This is called the local rate of change, and this term is called convective rate of change. Okay, so let's understand this Lagrangian description, eulerian description with one example. So let's understand with a problem. So let's say we are given a converging pipe let's say we are given a converging pipe. Okay, let's say these are my coordinate axes. Let's say this is x, let's say this is y, this is my center line, and we are given that the velocity on the horizontal center line, the velocity vector on the horizontal center line, v vector, is given as some magnitude u 1 plus x by l, where let's say this is x1 equal to 0 and this not x1 but x, so x equal to 0 here and x equal to l here. This length is l, 1 plus x by l times I hat. Okay, so this velocity vector we are given, and the question that we are asked is find the acceleration of the particle, find the acceleration of the particle along central line, along this center line, using a Eulerian approach, B Lagrangian approach. So by the way, should you get same values for the acceleration using both the approaches or not? Think about it. Keep the answer to yourself and let's see whether you are correct or not. Okay, let's start. So let's first find the acceleration using Eulerian approach. So in the Eulerian approach, we just derived that the acceleration is nothing but dv by dt, right? And in eulerian approach, this is equal to what? So this is equal to del by del t plus v dot grad times the quantity that we are measuring. So the quantity, the rate of change of which quantity we are measuring, it's the velocity. So we'll write velocity vector here. Okay, so now v vector is given to you, just put it here and find the value. Simple. So let's just find it. So so it would be del by del t, and since u is a constant, we can just keep it outside. Okay, so we have just plugged in the value of v vector in here and finding the answer. So del by del t 1 plus x by l I hat, so I hat will come outside, plus v dot grad. So again we have taken, since we have taken u outside, v vector will be given as 1 plus x by l I hat dot grad vector. Now grad vector has I hat, j hat and k hat, but the dot product of I hat will be non-zero only with the I hat term. So what is the I hat term? The I hat term is I hat del by del x. Okay, all right, and this is multiplied with v vector. This the v vector we have already taken inside. Okay, only this part is now multiplied with v vector. What is v vector? V vector is u. So we can see here that u will come twice. So since I have taken one outside, I will write one here. So u I hat del by del x, and what is v vector? V vector is this one, u 1 plus x by l I hat. U I have already taken here, so this will be 1 plus x by l I hat. Okay, correct? All right. So we are finding the acceleration vector using Eulerian approach. So this would be u, and I also forgot to mention that it is given that here this velocity so the flow is given to be incompressible and steady state. So incompressible means that the density is not changing as a function of space and time, and steady state means that this del by del t of the velocity is 0. Okay, so del v by del t we had here. So this was del v by del t if I don't take u outside, or if I take u outside, this will be divided by u. Okay, so this will be like this, and we are given that this is 0. So this term will become 0, and we are left with only this term. Okay, so what is I hat dot I hat? That is 1. What is, we have 1 plus x by l, then we have u, I hat dot I hat becomes 1, then we have del by del x acting on 1 plus x by l. So del by del x on 1 is 0, plus del by del x acting on x plus l would give you 1 by l. So this will become 1 by l I hat. So this will become u square 1 plus x by l, u square by l into 1 plus x by l I hat. So this is the acceleration of the particle using Eulerian approach. Okay, now let's see the acceleration of the particle from the Lagrangian approach. So B part, finding the acceleration from Lagrangian approach. Okay, so from the Lagrangian approach we don't have this knowledge, we don't have this knowledge, we just have a vector is equal to dv by dt. Okay, all right, and given that v vector is equal to u 1 plus x by l times I hat, let me just check it. Yes, so v vector is u1 plus x by l I hat, this is given to you, and we want to find the acceleration using just this knowledge of velocity vector. Okay, now in Lagrangian approach our velocity is only dependent upon time and not on the position vectors or the coordinates x, y, z. So then to calculate this we have to replace x with time. Okay, then only this v will be dependent only on time. All right, so how will we find it? So we can use the relation for writing x in terms of v. We'll use this relation that v vector is nothing but dx by dt, and this is given to be 1 plus x by l into y hat. Okay, if I just take the magnitudes, this will be dx by dt equal to u 1 plus x by l. So I can solve this differential equation. Okay, and this would be dt integrating x and integrating over t. Okay, so now integrating this thing will give me l ln 1 plus x by l plus some constant c1, and this will give me u times t plus some constant c2. So let's say c2 minus c1 is some other constant, and let's just write it as c. Okay, taking l this side, so c by l, let's say some other constant c3. Okay, and just simplifying this becomes 1 plus x by l equal to e to the power ut by l plus c3. Okay, and if I take 1 here this side, this will become minus 1, and if I take l also this side, this will become l times this thing. Okay, so my x is l times e to the power ut by l plus c3 minus 1. Okay, now given the problem of this converging pipe, this is given that this is x equal to 0, this is given that this is x equal to l. Okay, so this position vector as a function of time is only for this channel, right? So the time represents the x value for this channel only. Okay, this means that at t equal to 0 I should get x equal to 0, right or not? And at t equal to some t I should get x equal to l, because we are interested in the particle's position, the particle's motion inside this channel, and we are given this velocity vector. So we can argue that at t equal to 0 my particle should be at x equal to 0. Okay, so at t equal to 0, x is equal to 0, just put it over here, so it becomes e ut by l plus, so t is 0, so this will be 0, plus c3, so this is c3 minus 1, this is equal to 0, at t equal to 0, this implies e to the power c3 is 1. Okay, so if from this analysis, if e to the power c3 is 1, I can add this as x equal to L e to the power ut by L e to the power c3 minus 1, and e to the power c3 was 1. So I can just write e to the c3 as 1, and something into 1 is that something. So this x becomes this thing. Okay, so we use this boundary condition to get rid of this constant e to the c3. Okay, so this is my x. Now what will be my velocity? So v vector is, and this x is directed towards I hat, towards x-axis. So this will be my dx by dt. So it would be L d by dt of ut e to the power ut by L is u by L e to the power ut by L minus 0, because derivative of 1 would be 0, and I hat. Okay, so L gets cancelled out with L. We are left with u e to the power ut by L I hat. Okay, so this is my velocity. Alright, now since this is my velocity, my acceleration will be dv by dt, which is d by dt of this expression, of this term u t by L I hat. Now this u, since it is a constant, I can just take it outside of the derivative. I hat also I can take outside, so u I hat d by dt of e to the power ut by L would give me u by L e to the power ut by L. Okay, and this becomes u square by L e to the power ut by L. Okay, I hat. Now you can see that the acceleration that we got from the Eulerian approach and the acceleration that the acceleration that we got from the Lagrangian approach. So this is the acceleration we got from Lagrangian approach, and this is the acceleration that we got from Eulerian approach. So are the same? Let me just write it. Here. So this is the acceleration that we got from the Eulerian approach, and this is the acceleration that we got from the Lagrangian approach. So to compare them, we have to write x in terms of t, right? So we just found that x is equal to L, but x is equal to L e to the power ut by L minus 1. So just plug this x here, you will get u square by L 1 plus 1 by L e to the power ut by L minus 1. L gets cancelled out with L, so we are left with this thing. 1 gets cancelled out with 1, so we only get e to the power ut by L. And we can see that this expression and this expression is same. This is u square by L e to the ut by L, this is u square by L e to the ut by L. The magnitudes are the same, and also the vectors, right? So the value of the acceleration of the particle that we got from both the approaches are same, and this obviously must be the same, right? Because the particle is a particle, its acceleration has to be a single quantity. It cannot have multiple values, right? Okay, so I hope the difference between the Lagrangian and Eulerian approach is clear to you now. So we just saw that there can be so if you have some probes inside your, let's say, pipe, they give you some velocity vector, Okay, then from one approach, from Eulerian approach, getting the value of the acceleration was just, we could do it in just 2 steps, right? But from Lagrangian approach, it was a bit time taking to reach to that answer. Okay, so there could be some cases where, so there most of the times Eulerian approach is a better approach to find a value, to find the various quantities, like let's say acceleration, for our problem of interest. Okay, so I hope now the difference is clear to you. All right, now let me just give you a question which was confusing to me when I first saw this question. So the question is, think about rate of change of velocity, rate of change of position vector from both Eulerian and Lagrangian approach. So now we know that the relationship between Lagrangian and Eulerian approach is that, but let's just write it like this. So d by dt of some quantity q is given as del by del t plus v dot grad of that quantity q. Okay, so this is the Eulerian approach, this is the Lagrangian approach, and this is the Eulerian approach. Now we all know that dr by dt is nothing but velocity v vector. Okay, so this is what we got from the Lagrangian approach. Now in the Eulerian approach, we'll get del by del t v dot grad of r vector. Okay, so this gives you del r by del t plus v dot grad will give you vx del by del x plus vy del by del y plus vz del by del z, and r vector, which is xi hat plus yj hat plus zk hat in Cartesian coordinates. Okay, now what is vx del by del x of xi hat? This will be I hat, del by del x of x would be 1, so this will be I hat times vx. What would be del by del x of yj hat? 0. What would be del by del x of zk hat? 0. Okay, so this acting on these 3 terms would give me this value, plus now similarly this acting on this will give me non-zero term, which would be j hat vy, and similarly this will act on this term to give me a non-zero value, which is k hat vz, and here we have del r by del t, and this v vector we can further resolve, we can resolve in Cartesian coordinates. It will give me vx I hat vy j hat plus vz k hat. Okay, now what is del r by del t? Del r by del t is del x by del t I hat plus j hat del y by del t plus k hat del z by del t. And if I write this del x by del t as vx, this as vy, this as vz, what I will get? I will get vx equal to 0, vy equal to 0, and vz equal to 0, right? So is it correct? So this is the confusion that can come into your mind, that if I use this approach, like an Eulerian approach, for this position vector, I get Vx equal to 0, Vy equal to 0, Vz equal to 0, which means that there is no velocity vector, but there has to be a velocity vector, right? So then why am I getting Vx, Vy and Vz 0? So the answer to this is this that I wrote, del x by del t equal to Vx and del y by del t equal to Vy and del z by del t equal to Vz, this is wrong. And that's why these are non-zero. The reason is that in Eulerian approach, let me just write it, in Eulerian approach, the position vector are independent. They are not changing with time. So in Eulerian approach, if you remember, we fix a point and we see with time how the quantity changes across this point, right? So that's why in Eulerian approach, del x by del t, del y by del t, del z by del t, they are 0. And that's why if this is 0, so if this is 0, we'll get Vx equal to Vx, Vy equal to Vy and Vz equal to Vz. Okay. So let's just briefly summarize what we understood from this lecture. So we have just started fluid kinematics. We have just started fluid kinematics, in which our first topic is describing the fluid motion, and in this we studied two descriptions for the fluid motion. One is the Lagrangian approach, Lagrangian description of motion, and the other one is Eulerian description of motion. So we learned that Lagrangian description is when you concentrate on one volume element, which is also called parcel or sometimes also called particle. Okay, but let's not call it particle because otherwise it would become confusing with the actual particles inside the fluid. Okay, so that's why I'm just calling it as fluid element. So we concentrate on the fluid element and we track its trajectory with time. Okay, and in Eulerian description we fix a point. We don't care about whether the same particle is coming or not, or whether the same volume element is coming or not. Instead, we concentrate on one point and study what are the change in the quantities across this point over time. Okay, so we fix x, y, z and we see the change in quantity or the quantity in time t. All right, so this was this what we learned. What was the difference between the Lagrangian description and the Eulerian description. Okay, then we understood the relationship between Eulerian and Lagrangian descriptions, between these two descriptions. Then we considered one example to see if some velocity vector is given to me, then which approach gives me answer in less amount of time. Okay, so we saw that Eulerian approach gives us the answer quickly and Lagrangian approach took some time to reach to that answer. Okay, all right. So this was the way of describing the fluid motion. Okay.